Welcome back to this NPTEL online certification course in molecular arrangement and reactive intermediates. In the last couple of classes, I have talk about the carbocation, and then I talk about the carbon ion, and then carbene, nitrene, and free radicals, and also benzene. Then I thought about talking about metallic compounds. So there are briefly I am going to talk about organolithium, then the Grignard reagent, then the organozinc, and organocopper. But before I go and talk about them, I am going to briefly introduce you the history of organometallic compounds. I am going to talk about some of the how the organometallic compound started, and then I am going to take you to the organolithium compounds. Their the basic concept, their structure, and some of the basic reactivity. Okay, so let's start with the discovery, the early discovery of the organometallic compounds. It was the 1760 when the cadet was working on the cobalt containing inks, and then he found out later a compound called the cacodyl oxide. Okay, and he found this compound called the tetramethyl diarsine. So which is here, you can see the arsenic with 2 methyl group here, and the arsenic there is a bond here. And then this is the other compound with the oxygen, which is the the cacodyl oxide. And then in 1827, it was the first pi complex, which was the JSA salt was discovered, the platinum with the the 3 chlorine and the pi bond. Then Franklin actually introduced the term organometallic in 1850, and also there are several organometallic compounds, several organometallic compounds which are air and moisture sensitive, was actually synthesized using the mercury and tin, like diethyl zinc, diethyl mercury, and then other reagents. So now I am going to briefly define what is called organometallic. So organometallic chemistry is study of chemical compound containing at least one bond between a carbon atom and a organic compound. So that is the important thing. You see from the terminology organo and metallic, that means there will be organic part, means something attached with a carbon, and there will be a metal. And then they provide a source of nucleophilic carbon atoms, because you can see in this, when it is attaching with the metal, always the carbon is going to be the one which is going to be the nucleophilic. And so what is going to happen, it is going to found and going to another electrophilic carbon. So that carbon which is nucleophilic in organometallic compound going to react with a other carbon which is electrophilic in nature. So they can form a bond. Of course, there are a lot of different organometallic compounds. You can think about the organometallic compounds from the main group elements or from the main block elements, and they are from the tangential metal elements. Okay, so then I'm going to show you some of the example in this particular class. My plan is to talk about these 4 different type of organometallic compounds. One is the organolithium, organomagnesium or the Grignard reagent, then organocopper, and then organozinc reagent. Of course, this the metalloids like silicon, tin, and boron containing compounds also called organometallic compounds. Okay, so you are going to also see, I am going to discuss about the organoboron chemistry as well. So again, you can classify them as ionic organometallic compounds or covalent organometallic compounds. There are 2 different class. So from the terminology, you can clearly understand if it is ionic, then what is going to happen. You see there is mostly from the alkali and alkaline earth metals. It means lithium, magnesium, those are the things we are talking about here. And they have maximum ionic character. That means these are mostly in the form of like a C minus and M plus form. And then there is other type of organometallic compound is called covalent organometallic compound. You are going to find a lot of these tangential metal complex, and you have seen, you have studied there, are actually in the class of covalent organometallic compounds. So then I am going to try to give you a brief idea about the differences about this type of organometallic compounds. So the thing is, if you think about a carbon with a metal, so let's try to understand forms like about a covalent bond. If you think about, we are forming a bond between this and this is a covalent bond, then the polarity is the another important factor we have to consider. The polarity of the covalent bonds, correct? This is a very important thing. And let's try to understand from the basic carbonyl compound. So if you think about a carbonyl carbon and an oxygen, and if you try to think about the polarity, then you always know that the oxygen has electronegativity of 3.5 and the carbon is 2.5, and there is a 1 electronegativity difference between the oxygen and carbon. So because oxygen is more oxygen is more electronegative. So what is going to happen? It is going to pull the electron density towards oxygen. So you will see there will be some sort of a delta plus charge in the carbon and delta minus in the oxygen. Now if you come to an organometallic compound like organolithium or any type of carbon with a metal. So what you are going to see here, generally in case of the lithium, the carbon have electronegativity 2.5, lithium is 1.0. So what is happening here? You see something reverse from this here. What you are seeing here, the carbon having actually a delta minus or a negative charge, and the lithium is a delta plus. Okay, and you can see there is a huge difference. There is a 1.5 difference. So that means the most of the electron density of this carbon lithium covalent bond actually lying on the carbon atom. Okay. So that's why you see that in case of this type of methyl lithium, it's mostly like a CH3 minus, you can think about. So I'm going to talk about all these different type of, as I mentioned, I'm going to talk about the organolithium reagents. I'm going to talk about their synthesis, how you can synthesize from this corresponding alkyl halide. There are also other methods. And then going to the Grignard reagent, using the magnesium, how to make the Grignard reagents, what are the different mechanism for the synthesis of Grignard reagent. Then organocopper reagents, of course the one of the important one is the Gilman reagent, how you can make the Gilman reagent, and what are the different reaction using Gilman reagent. Then about organo zinc reagent, what are the difference between and then what are the difference between these four, about the organolithium and organomagnesia, which is more stronger or more weaker, and if this is stronger, then what is the difference between their reactivity. So we are going to discuss all these different things in this particular topic. So we are going to start with the organolithium. So you can see first organolithium reagents is react with wide variety of organic substrate. As you can see, this is a kind of a carbon with a minus. It can able to react with different compounds. So it can act as a base as well as it can act as a nucleophile depending on the structure. Okay, and then what is going to happen? So most organolithium reagents are prepared in a hydrocarbon solvent. So as you see, if your organometallic species is very reactive, you want something not something a polarizable group are there, or something can be deprotonated. So you want some sort of a solvent where it will be not going to react with the solvent, that you have to be. So that's why hydrocarbon solvents are most you find. If you are purchasing them from any Sigma or any other supplier, you will always see they are in the pentane or in the hexane. Okay. Okay, and the important thing think about, if you have an organolithium, we are talking about terbibutyl lithium or tertiary lithium, you can say secondary lithium and primary lithium. So if you have this primary to secondary to tertiary in the organolithium, what is the difference between them? Let's talk about their pKa first. From the pKa value, we can clearly see going this direction, the pKa getting decreases. So what is happening here? You can see from the structure wise, this organolithium, terbibutyl lithium is bulkier compared to a n-butyl lithium, or if I can write methyl lithium here. So that pKa is around 48. So what is happening here in this direction? You can see pKa is decreases. That means we know from that if you have a base the pKa decreases, that means the basicity getting decreased. So this way the basicity getting decreased from terbibutyl lithium to methyl lithium. But if you talk about the nucleophilicity, or if you talk about the reactivity, that will be reverse. The reactivity will be highest in methyl lithium. Okay, and then the n-butyl, then the seg-butyl, then the terbibutyl lithium. Okay, because only difference is that. So in case of, you can see here, the size is the another important factor. If it is a bulkier, then it is mostly going to act as a base instead of a nucleophile. We are going to learn the molecular orbital diagram. So this is nicely given in the Claydon book. If you are following that book and go to the organometallic chapter, you find that diagram is given. So what they are talking about from this diagram, that if you talk about this carbon and lithium bond, so this is a covalent bond. So if you think about this covalent bond here and try to go for the molecular orbital, then what is happening? The 2s atomic orbital for the lithium and the 2p orbital from the carbon is forming this sigma bond here. So now if you see about the energy difference, this sigma electron density is mostly in this p orbital on that particular carbon. So that is also clearly seen from the molecular orbital, that sigma bond electron density is actually on the carbon. because carbon is the one which is the closest one, and the lithium is far from here. So that's why you are going to see that the mostly the charges are actually on the top of the carbon, the negative charge. Okay. So the other important thing about the I think this is a question we always ask ourselves, that when you talk about this organolithium region, that okay, we are talking about RLI, it could be a methyl lithium or it could be n-butyl lithium. The question always comes, does it really stay like n-butyl lithium or it has some other structure? So we always see about, once we find in a solvent, we find in a aggregation. So they actually stay as a aggregation. What is the aggregation means? Because you have this electropositive charges, electronegative charges, because if you are using a diethyl ether, you can understand the ether oxygen can form a bond with the lithium which is electropositive, correct? So it can be a Lewis acid base in adduct, some sort of oxygen can give in lone pair forms adduct with the lithium. So that's how what is happening, depending on the solvent, you will find them, they are forming different sort of aggregations. Okay. So that so this type of aggregation depends on couple of things: what solvent is there, and what type of organometallic species we are talking about. Is it a primary organolithium or an organometallic reagent versus a secondary versus a tertiary. So these all the factors are important. And then based on that, you are going to see a couple of different things. You are going to see tetrahedron or octahedron metal cores going to form. So here lithium 3 triangle going to, so this is a lithium 3 triangle, and then after the lithium 3 triangle you will see different type of solvent going to form these aggregates and form the different type of shape. It could be a tetrahedron or could be octahedron, or could be something like, in case of methyl lithium you will end up seeing something like cuban type clusters. Okay. And now you are going to see that what are the, why there are different shapes. Again, I was telling you at the beginning, the most of the cases you see the hexameric aggregates are found. Okay. But then the primary alkyl lithium turned out to be the tetrameric unit. Again, as I mentioned, these shapes are mostly, you cannot really predict that okay, if you take this particular unknown lithium and you put the solvent, you can say okay, this will be tetramer or dimer. No, there is no such prediction or no such model. Mostly people have find out from the X-ray structure, from the different aggregation. From there we can able to write them. Okay, it could be a tetramer or it could be a hexamer. Okay. So you can see primary alkyl lithium mostly go for tetrameric unit. If you have a tertiary alkyl lithium or where alkyl groups are bulky, it end up form a tetramer and a linear aggregation can happen. If you have a really bulky, it can form a linear aggregation. And in a lot of the times you also find in case of the secondary or in case of the primary, depending on the solvent, they can also form some sort of a hexameric aggregation as well. So there is a list here, you can see in case of methyl mostly you are seeing this tetramers in THF and HMP. So there are a list of some of the common solvents, you are able to purchase them. In case of n-butyl there is a hexamer happening in case of pentane. Once you have a ether, it is forming a tetramers. And so again these are the structure which was found and from the X-ray, and that's why it was written here. Again, there is no hard and fast rule that what type of structure they are going to form. Again depending on the solvent, you can see same n-butyl lithium, depending on the solvent it can form a tetramer or it can form a hexamer. Very similar thing happening in case of sec-butyl or in case of tarbutyl lithium. Sometimes in case of tarbutyl, if you are in the THF solvent, it can form a monomer, means depending on the solvent, because what is going to happen, solvent is going to make another important thing here, because depending on the solvent structure and depending on how the solvent is forming a coordination with your lithium, these shapes are also depending on that. Another important fact, I think the students always ask this question, that when you doing organolithium reagent, why we have to go to a low temperature, like sometime minus, I think mostly you see we are doing in minus 78. Why that is necessary? So one of the important fact is that for some solvent, like if you talk about tetrahydrofuran, which you might mostly use if you try to do a organolithium chemistry in the lab, then this type of solvent, once you increase the temperature, if you are not doing a minus temperature, if you are coming to the a room temperature or maybe, so I think so this type of THF started breaking out. So what happens, your solvent is going to break down and it is going to form a ethylene and this lithium enolate, some sort of a enolate going to form. Okay, so it is going to break down through such mechanism and then it is going to form this type of species. So that is why we try to do this reaction at very low temperature, because we don't want the solvent to be decomposed, because then what is going to happen, this can also take part, this can mess up the entire reaction. And there is another mechanism also, that it can form after the lithium formation happening. So first thing is, once you increase the temperature, this is the proton going to abstracted. So that is going to form this corresponding lithium, and from there only you can able to see alpha elimination, or it can form this type of species here, ethylene and this lithium analyte species, or it can able to go for alpha elimination and then going to form this type of species here. Okay. So what are the common solvents? If you try to use this organolithium reagents, then we generally use diethyl ether in the lab, or THF, DME. These are the solvents. Of course there are more, but these are the very common solvents. And a lot of the times you are going to see that in the lab we are also using some additives. If you are using organolithium reaction, then we also sometimes add some additives, like we add additives called timeda, a tetramethyl ethylene diamine, or it could be a pentamethyl. Okay. So you can see we can also use a HMPA, or it could be DMPU. So all the different type of so you can see here, so these are nitrogen based compounds here, and so we use in this type of compounds in the reaction as a additives. Okay. So now the question comes, why we have to use this additives in the reaction? What is the role of these additives? So first you have understand that this type of organolithium reagents, when you are finding in the corresponding solvent, like mostly you find they are in the pentane or hexane. So in this or in ether, so they are actually forming a aggregate, correct? We already talked about it. Now if it is aggregate, then the lithium is not that reactive. So what we try to use, we use this type of reagent, this type of timeda, or you have seen the HMPA. What is going to happen? Those nitrogen going to make a complex with your lithium. So those two nitrogen of the timeda, you can think about. So they can make a complex with your lithium. Once they will get the lithium out, it can go for a decomplexation. That means from the aggregate, it can form a smaller complex, and it will make your anion free for reacting. That means your organolithium will be much more reactive once you form this aggregation. Okay. So it also does one important thing. It is also going to stabilize it. Okay. So that is the important thing is. So important thing is, it actually is a bidentate thing. So it forms a chelate with your lithium. It increases the nucleophilicity. Okay. And there are different things, as I mentioned. And again, you have to use them also in a stoichiometric amount. That is also another important thing. If you are using one equivalent of them, you should also use 1.5 little more, so that you make sure all of your lithium forms some sort of a chelate. So these are the common things you buy from this store. So it comes with a particular strength, n-butyl lithium, sec-butyl lithium, or phenyl lithium, tributyl lithium. You can able to buy from the store, and they come with a particular strength. And I'm going to also teach you in the later classes that you can also use some sort of a titration method. There are several different methods to titrate them, that you have to find out what are the strength of these organolithium reagents. So again these are ionic in nature. Again due to the small size of lithium, there is greater polarizing powers, and they are extremely reactive. So again I think sometimes they are not only, they are also pyrophoric. If you talk about the tributyl lithium, these are also pyrophoric, because these are very much reactive. Again the reactivity of organolithium compounds toward the air and water. So we are talking about that this type of compounds are actually moisture sensitive and air sensitive. What that is mean? That means if you take the organolithium compound to a water, what is going to happen? It is going to form lithium hydroxide and corresponding alkane. So that's why you have to make sure that, of course, you can understand clearly this is a kind of some sort of a carbon ion. So if you have a water, it is going to quench it. And if you take a oxygen, what is going to happen? If you found oxygen with organolithium like n-butyl lithium, it is going to form the lithium n-butyl peroxide, and finally it is going to make lithium n-butoxide, or you can say the same compound as a lithium n-butanolate. Okay. That means again you have to understand these are the compound, it can react with the moisture as well as with the air. So the other important parameter we should understand that once you are talking about different organometallic reagents, We talk about the organopotassium is also there, organosodium, organolithium, organomagnesium. In this direction what you are seeing the percent, so there is a percentage of metallic character. As the percentage of metallic character increases from the magnesium to lithium to sodium to potassium, your reactivity getting increased. So if you think about, if someone asks you that if you have a organic sodium compound versus a organolithium compound, then of course the sodium and potassium will be much more reactive compared to your organolithium. And again, if you compare organolithium with organomagnesium or the Grignard reagent, then organolithium will be much more reactive than compared to the organomagnesium because of the percentage of ionic character. Now I am going to talk about that, as I mentioned that organolithium reagents, all cannot be act as a nucleophile, they can act as a nucleophile, or a base. So that is also depend on their size. So that means if you have a organolithium reagent, like I am going to mention a LDA, then lithium TMP, so it's a tetramethyl pyrrolidine. Then you can see LHMDS. So you can see here what is the structure here. You have N lithium, and then in this side you have silicon. So it's a hexamethyl disilane. Okay. So again, if you see this characteristic of this, and here what you have isopropyl. We always talk about that. We call it, okay. So now if you see about this structure, one of the important thing is these are really this next to the lithium, this carbon has a hinder, correct? In case of lithium TMP or in case of LDA, you see there is a bulkier group, or in case of here two silicon groups are here. So because of this bulkier group, this type of organolithium species, you can see their pK values. So this is pK 30, 37, 38, these are quite strong base, correct? So these are commonly used for a deprotonation. You will see this base are using for the deprotonation purpose. And because of this bulky structure, they are mostly used as a base instead of a nucleophile. Again, if you talk about N-butyl lithium, then in case of N-butyl lithium or methyl lithium, you will see them, what is going to happen, they mostly act as a nucleophile instead of a base, because again organolithiums are very hard, so they can able to go for 1,2 addition, which I am going to explain also. So first thing, they actually participate in many different reactions, and they act as a base, as I mentioned. So that means if you found out that you have some sort of a organolithium reagent and you have a acidic proton, like you have a proton of this this carboxylic acid, then first thing will be there will be deprotonation going to happen. And of course if you use excess, then it's going to attack. So if you have a aldehyde here, it is going to attack here, form the corresponding O lithium. If you put H2O, or then it is going to form the corresponding alcohol. Again I am going to come back to some of this in a specific example. It can also, if you have a alkyl halide, then it can go for a metal halogen exchange to generate a corresponding lithium. Then it can have a metal metal exchange, that means it's called some sort of a transmetallation can happen. If you have a organotene, if you use organolithium, it can generate a lithium reagent through a transmetallation, or it could be a ortholithiation. We are going to spend a lot of times on this particular topic, that if you have some sort of a directing group where lithium can able to bind, then it can direct the deprotonation from the next carbon, and then this CH bond going to get deprotonated to form this corresponding lithium. So as they are strong base, what is going to happen, they can abstract proton from water, from alcohol. You can see, because I think you guys are very familiar with the pK chart. So you can understand, these are the base from 30 pK, starting from pK 30 till it is going up to 55. So that means there are lot of these things, lot of this proton from in this range, which all of them going to get deprotonated starting from water. So you can see phenols, anilines or amines, alkynes, dithions, protection, all going to get deprotonated. They are also good nucleophile, as I mentioned. If you are using this type of alkyl alkyl lithiums, they are very good nucleophiles. They are going to add to all this, aldehydes, ketones, acid chloride. Then it can also add to the cyanide, and every cases in the former one you end up getting alcohols, and you can add to acid chloride. I am sure it's not going to stop here. It is going to add 1 mole lithium and end due to the corresponding alcohol. If you add to the cyanide, it is going to add here, then going to hydrolyze to corresponding ketone. It can also add to the corresponding imine, then it can protonate here and then go to the corresponding amine here. So I think I am going to spend some time in this part, and in the next lecture what are the different method for the preparation. So one of the important method is for the synthesis of organolithium reagent is using a metal halogen exchange, or some books they mention it as a oxidative addition. So let us try to understand what is happening. If you have a alkyl halides and if you take a lithium wire, again you can purchase the lithium wire, which can be sold as a lithium wire in kerosene. You can chop this lithium wire and you can do the reaction using alkyl halides that can generate corresponding alkyl lithium. Okay. So now you can think about why they are saying this is a oxidative addition, because of the change of the oxidation state. Correct. What is happening? You see there is a clear change of oxidation state is happening. So that's why it is saying some sort of oxidative addition, but mostly I tell this type of reaction as a metal halogen exchange, because at the end your halogen is replacing and you are introducing a lithium here. So there is some example here. You can have this cyclopropyl bromide. It can N-butyl lithium can also able to do that. Instead of the lithium lithium wire, you can also use a another organolithium reagent which can able to do the job to generate this type of organolithium species. It can be corresponding bromobenzene, can also same thing can happen. From bromobenzene you can generate the corresponding phenyl lithium. Then there is a carbon ion and halide exchange. So suppose if you have a corresponding organolithium reagent, and if you take the magnesium halide, that can generate the magnesium Rx and the lithium X. Okay. It can also react with the magnesium halides. I think the most other important method among all of this is the deprotonation. You are going to see a lot of this discussion about these topics in the next class, where you are going to see there are a lot of different protons, because as you see it's a very strong base. It is going to deprotonate a lot of the acidic proton you will see, and then it is going to generate the corresponding organolithium, because once the deprotonation is going to happen, it will be generated minus and the lithium plus. Okay. So we are going to talk about a lot about this. So there are different type of method, and you will see there will be different type of proton. It could be sp3 or it could be sp2. So this proton could be attached with a sp2 carbon or with a sp3 carbon. So we are going to discuss in details this part. Then there will be a transmetallation. We are going to talk about them in a lot. So we are going to show that this can transmetallate with tin and some other with selenium. You are going to see. So in this particular part, I think I try to talk about about the definition of organometallic compound. I try to talk about what are the difference if you have a if you have a organomagnesium versus a organolithium versus a organo copper, organo zinc. Then also I try to talk about the important thing is the polarity. What is the why the organolithium compounds are so reactive, where the sigma bonding is lying. Then also I talk about one of the important thing about aggregation, about the organolithium reagent, what are the different aggregated structures. Then the role of the TMEDA or the additives what you use for the organolithium reaction. Of course, one of the important thing you have understood in this class is the basicity versus nucleophilicity. So depending on the organolithium reagent, you can see one cases it is going to abstract a proton, and in other cases it is going to go for a 1-2 addition. I am going to discuss this particular topic, the preparation of organometallic reagents, in details in the next classes. Okay. Again these are the references here, and again thank you for coming to the class, and I am going to see you guys in the next class. Thank you.